last time we stopped here, talk about different type of errors. Okay. All right, this is the slides here. Okay. So there's two types of errors which may occur in a statistical test. Okay. So this is, for example, the actual fact could be 1, H0, the null hypothesis is true. Okay. If that's the case, we're gonna accept H0. Okay. Or H0 actually is false. Okay. But the decision, the conclusion of our calculation could also be either H0 is true or H0 is false. Okay. If H0 is true, we said we fail to reject H0. If the actual fact is same as our decision, for example, H0 is true and H0 is true, so our conclusion is correct. And same thing, if the actual fact is H0 is false and our conclusion is H0 is false, we also make the correct decision. Okay. So two errors is here. The type 1 errors occurs when we conclude H0 is false when H0 is actually true. Okay. And type 2 errors is the opposite. Okay. Type 2 errors occurs when we conclude H0 is true, but actually H0 is false. Okay. So that's a two type of errors here. And type 1 errors is controlled by alpha, okay, which is the probability we reject H0, but actually when H0 is true. Okay. The type 2 errors is called beta, okay, which is probability when we fail to reject H0, but it is actually false. Okay. And of course, we want to keep the probability of errors as small as possible. Okay. And the value of alpha, as we discussed last time, is the significance level. Okay. And this alpha can be controlled by us, experimenter. Okay. But the value of beta is very hard to control. It's almost impossible to calculate the beta. That's the reason we want to, control the type 2 error. Okay. So rather than accepting H0 as true without being able to provide a measure of goodness, okay, we choose to not reject H0. Okay. Because again, it is easier to control the type 1 error. Okay. Easy to control. Okay. This is what we're not doing. So because the type 2 error is hard to control. Right. Here is the example. We have a scale. Is to be calibrated by weighting 1,000 gram test weight 60 times. Okay. And we have 60 scale reading with the mean value of 1,000.6 and standard deviation of 2 gram. Okay, so we found the p-value for the testing. First of all, we set up the null hypothesis H0 and the alternative hypothesis H1. Okay, the equality line always go with H0, so we set up like this. The population mean is equal to 1,000, okay, which means the reading is same as the weight of the tests. Okay, so the scale is accurate, or the mean value is not equal to 1,000. Okay, which means the scale need to be recalibrated. So the null hypothesis H0 specifies the mean, the population mean reading is equal to 1,000. Okay. So the value of the sample mean that either much larger or much smaller than mean will provide evidence against H0. Okay. So we assume H0 is true. Okay. So the sample reading is assumed to draw from the null hypothesis, the null distribution, which is a population with a mean value of 1,000. And we do not know the population standard deviation, but we can use the sample standard deviation S to replace sigma. Okay. So we get the null distribution, okay, with the mean value of 1,000 and standard deviation of S over square root of sample size n. Okay. So we get standard deviation and the mean value. So then we calculate z-score, and the probability we observe a value of 1,006 if we assume the null distribution is correct. Okay, so we calculate z-score based on the equation x minus the mean value divided by the standard deviation. So the z-score is 2.32, which is pretty big. If we use the z-table, table 8.2, we found out the probability will be very small, actually only about 2%. Okay. Because the H0 specify mu equal to 1,000, so we need to use the regions on both tail of the curve. Okay, which is here. We need to use the value on both tail of the curve. Okay. There's some other case which the H0 specify the mean value larger or smaller than a certain value. In that case, we're gonna only use one-sided tail. Okay, so we're gonna discuss that in a moment. But here we use the two-sided based on a z-score of 2.32 and minus 2.32. So the p-value is 0.0102 times 2, which is 0.0204, so about 2%. Okay, so the p-value is only 2%. So we can see if we assume A0 is true, then the probability we observe an average of 1,000.6 or even larger than that value, more extreme than that value, is only about 2%. So the chance is very small. So p-value actually is only 2.04%, 2.0204%. So the evidence against H0 is very strong, so we can see it is okay to reject H0, and we can conclude H1 is true. Okay, and H1 is here. Okay, so the population mean reading is not equal to 1,000. So we need to recalibrate the scale. Okay. So we need to recalibrate the scale. All right. So when the null hypothesis specify a single value, in the previous case, mean value is equal to 1,000. Okay. Then we should use two tails. So both tails, left tail and the right-hand tail, need to be used to calculate the p-value. Okay. So we call that two-sided or two-tailed test. But sometimes A0 only specify the mean value is larger or smaller than a certain value. So larger than or equal to or less than or equal to a certain value. Okay. So mu large or equal to mu 0 or mu less or equal to mu 0. So if that's the case, we're going to use one-sided test. One-sided test. So let's look at another example. All right, so we have a high airline occupancy. So high airline occupancy rates on scheduled flight are essential to corporate profitability. Okay. So suppose scheduled flight must average at least 60% occupancy in order to be profitable. Okay, so if less than 60%, it is not profitable. Okay. And examination of occupancy rate for 110 a.m. flights. Okay, these are the details from Atlanta to Dallas. Shows result that the mean value is only 58%. Okay, so that is less than 60%. And the standard deviation is pretty high, 11%. Okay. If the mean value is the mean occupancy per flight, okay, and if the company wish to determine whether or not this scheduled flight is unprofitable, okay, so this is the question asked, whether or not the scheduled flight is unprofitable. Whatever the question is asked, we should use that as H1. Okay, so H1 as what the question asked. All right, and then the opposite will be H0. Okay. So the question asks us to draw the null and alternative hypothesis. So because the question is asking if the scheduled flight is unprofitable. So unprofitable means mu less than 60%. So the occupancy percentage is less than 60%. So that will be H0. Okay. So H1 will be the opposite. So the null hypothesis H1 will be mu large or equal to 60%. Don't forget the equality line. So this is the setup. So that's one thing. So H0 is what the question asks. The second one, the equality line goes with H0. Okay. So these are two important rules you want to use when you set up the hypothesis test. Okay. All right. Okay. Second part, do the occupancy data from the 100 flights suggest that this scheduled flight is unprofitable? Okay, so tell us the alpha is 5%. So what we're gonna do is we calculate the z-score first. Okay, the z-score based on a null hypothesis. So we get an average of 58%. Right? Okay. All right. So 58% minus the no distribution mean value for the no distribution, which is 60. Okay. Sample standard deviation at 11. Sample size is 120. So we calculate the z-score. Sorry. Okay, here. Okay. So the calculated z-score for that is around -2. Okay, minus 1.99. Okay. Then we go to table 8.2. All right. So this is the z-score, z table. Okay. Right. For minus 1.99, the p-value here, the p-value is equal to 0.0233. Okay. So again, this is based on the table 8.2. So 0.0233 is less than alpha, which is equal to 5%. Okay, so p less than alpha, we can reject H0. Okay, so we see H1 is true. And H1 is set up as the airline is unprofitable. So suggest unprofitable. Okay, so this is another example. So in summary, here is a procedure. If the sample size is large, okay, there's some other equations depending on the situation, such as small sample size and what the question is asked. But here in section 6.1, for large sample, it's coming from population with a mean value and a standard deviation of sigma. Okay. If H0 is set up as these three scenarios, so mu less or equal to mu 0, large or equal to, or equal to. Okay, so notice the equality line always goes with H0. Okay, again, equality line always goes with H0. Then we calculate the z-score, okay, based on this equation. Okay, if we do not know the population standard deviation, we use the sample standard deviation S. Okay, so that's the setup. Then we calculate the p-value. Okay, the p-value is areas underneath a normal curve. Okay, normal curve based on a z table, depending on how H1 is asked. So if H1 is asked mu larger than mu 0, then the p-value will be the area to the right of z, to the right of z, which is this area. If H0 is set up as mu less than mu 0, then the p-value should be the area to the left of the z. Should be here. If H1 is mu not equal to 0, mu 0, then it should be a two-sided tail. Okay. So based on that, and table 8.2, we calculate the p-value. And then we just compare the p-value with alpha. Okay. If the p-value is less than alpha, we can reject with 0. Then we say H1 is true. Okay. So based on how the p-value compared to alpha, if the p-value is not than alpha, we fail to reject with 0. or p-value less than alpha, we can reject H0, and we see H1 is true. H1 is true. Okay. We have another approach, okay, which is based on the critical value, but this is not as commonly used as the p-value approach. So we use this one normally. Okay. All right. So let me know if you have any question. So that's section 6.1. Let's continue. Okay. There's two possible conclusions based on compare p-value with alpha. Okay. So if p-value is less than alpha, we're gonna reject H0. Okay. So we can conclude H0 is false and H1 is true. Okay. Or if the p-value is larger than alpha, we cannot reject H0. Okay. So in other words, we see H0 is plausible. Pay attention here. We cannot say H0 is true. Actually, we can never conclude H0 is true. Okay. The reason is because the p-value is a probability. If we assume H0 is true, what is the chance we observe that certain value from the experiment? We can never conclude H0 is true. Okay. We can just see it is plausible. Okay. And we also need to know the level of disagreement, which is measured by the p-value, and compare the p-value with alpha. Okay. If the p-value is great enough, if the p-value is larger than alpha, then the null hypothesis is implausible. Okay. And the smaller the p-value, the more certain that H0 is false. Okay. And the larger the p-value, it is more plausible H1 become. Okay. But again, we can never be certain that H0 is true. Okay. Okay. So if the question doesn't tell us on alpha, typically we use 5%. So when the p-value is less than 5%, then we're going to conclude we reject H0. Okay. But this rule doesn't have any scientific basics. Okay. For example, in the previous example, the mayor claimed the average income of the city is equal to $35,000. Okay, and we get a sample, and the sample mean is only $30,000, far away from his claim. Okay, so the p-value calculated based on that is very, very small, okay, nearly zero. So we conclude if the claim of mayor is true, the chance, the probability we observe such a low mean value of $30,000 is almost impossible. Okay, if, for example, the mean value of a sample we got is $34,000, which is much closer to the claim, which is $35,000, then the p-value will be high, much higher actually. Okay, then we cannot reject H0. We're gonna say H0 is plausible, but again, we can never conclude H0 is true. So we can never conclude the mean income of the city is $35,000. So when the p-value is less than alpha, the threshold, then the result is said to be statistically significant at that alpha level. Okay. So if p is less than or equal to 5%, we can see this result is statistically significant at 5%. If p is less than 1%, then we see it is statistically less significant at 1% level. Okay, so actually alpha can be any level. Okay, so if the test is statistically significant at 100 alpha percent level, for example, if alpha is 0.01, then it can be 1%. Okay, so we can also see the null hypothesis is rejected at level 100 alpha percent. So the null hypothesis is H0. So let's see, we have hypothesis test, okay, and the null hypothesis H0 is mu equal to 0, and the p-value we calculate is 3%. Okay, so is this result statistically significant at 10% level? So alpha is 10% here, so p is 3%. So because 3% is less than 10%, so p less than alpha. So yes, the result is statistically significant at 10% level. How about 5% level? So alpha right now is 5%, but p is still less than alpha. So it is still statistically significant at 5% level, but not 1% level, because p is larger than alpha now. Okay, so it is not statistically at 1% level. Is the null hypothesis rejected at 10%? Yes. At 5%? Yes, but not reject at 1% level. So in summary, if p is less than alpha, then we say it is statistically significant. And then we conclude H0 rejected and H1 is true. Okay, so that's the steps. So here's some more comments. Sometimes people only report a test is significant at certain level, but without giving the p-value. This is not a very good approach. We should always give the p-value. So this is not good without giving the p-value. There are some reasons why this is bad practice. Okay. First of all, they give no way to tell whether the p-value was just barely less than the alpha or not. Say the alpha is 5%. If the p-value is 0.049, so this is barely smaller than 5%. So this is statistically significant. Okay. Same conclusion we can draw for the p-value of very, very small. Okay, it is also statistically significant at 5%, but there's a difference between these two p-values. Okay, so that's one reason. Another reason is it suggests there's a big difference between a p-value just under 0.05, which, for example, 0.49, and just above 0.05, 0.051, for example. So these two p-value is very close, but if we choose 5%, one is statistically significant, the other one is not. But actually, that's a very small difference between these two. Okay, because p-value is not given, so whether p-value is small enough to reject no hypothesis, the readers cannot do that. Okay, so that's the reason we always should give the p-value. Okay, so reporting p-value give more information, and it allows the reader to decide whether to reject the null hypothesis or not. So always give the p-value. Okay. So in summary, if alpha could be any value between 0 and 1, but normally it's around 1%, 5%, sometimes 10%. If p-value is less or equal to alpha, okay, we said the result of test is statistically significant at that 100 alpha percent level. Okay, and then H0, the null hypothesis, is rejected at that level. Okay, and we report the hypothesis test. Also, remember include the p-value. Okay, is statistically significant or not at whatever alpha. All right, let's talk more about the p-value. Okay, we know p-value is a probability. Okay, and a small p-value indicates that H0 is unlikely to be true. Okay, so some of us may think that the p-value is the probability H0 is true. Okay, but this is not the case. Okay, the p-value actually is that. So p-value is the probability of observing, for this example, a sample mean value of a certain value under no distribution. Okay. Observing a sample mean under no distribution. This is different from the probability A0 is true. Okay. Actually, A0 is true or not true. Okay. It's already there. Okay. So the truth or false of A0 cannot be changed by repeated experiment. Keep in mind, this is what the p-value really means. Okay. P-value is not the probability H0 is true. Okay. To explain this concept more, let's go back to the previous example. The mayor said the A0, the mean income of the city is $35,000. Okay, and a sample of, I don't know how many, maybe it's 50 people, the average income is $32,000. Okay, so the p-value we calculate based on that z-score is a probability that we get a sample of average $32,000 if we assume a mean value is actually $35,000. Okay, so that is what the p-value means. Okay, again, the p-value is not the property that H0 is true. Okay, and the next two slides is very important. So that tells us how we set up H0 and H1 and why we set up like this. Okay, so let's look at this example. So we have specs for water pipe call for a mean breaking strength mean value of more than 2,000 pounds per linear feet. Okay. An engineer will perform a hypothesis test to decide whether or not to use a certain type of pipe. Okay. So they select a random sample, okay, and measure the breaking strength and perform a test. So the pipe will not be used unless the engineer can conclude that the mean value is larger than 2,000. Okay, so let's see the setup like this. So H0, the null hypothesis is mean value less or equal to 2,000. Okay, the equality line goes to H0, that's good. But this is less or equal to 2,000. So H1 will be mean value larger than 2,000. So will the engineer decide to use the pipe if H0 is rejected? Okay, so if H0 is rejected based on the calculation, so if rejected H0, and then we can see H1 is true. Okay, so H1 is true means the mean value will be larger than 2,000. Okay, so the conclusion is good. So we use the pipe, right? But if the H0 is not true, if H0 is not, the p-value is larger than alpha, H0 is not rejected. Okay, and then we conclude H0 is plausible. Okay, so the mean value might be less or equal to 2,000. Okay, so the conclusion is now use pipe. Okay, so this is good setup because based on the result, whether H0 is rejected, we can conclude whether to use pipe or not use pipe. Okay. The next one is a bad setup, the same question, but we set up as this. So H0 is mu larger or equal to 2,000. So equality line also go with H0, that's good. But this is H0 is mu larger or equal to 2,000. And H1 is less than 2,000 for the mean value. Okay, so let's see whether the engineer can decide to use the pipe or not. So if H0 rejected, then we conclude the mean value is less than 2,000, right? We conclude H1 is true, so mu less than 2,000. So we cannot use pipe. Not use pipe. On the other hand, if H0 is not rejected, okay, then we say H0 is plausible. Okay, so that means the mean value might be large or equal to 2000, but also might be less than 2000. Remember, we can never conclude E0 is true. So what is the conclusion here? So we are not sure enough the mean value is larger than 2000, so we cannot use the pi also. So in this case, no matter what A0 is rejected or not, the same conclusion is just not use the pi. Okay, so that is a bad setup. Okay, because it draws the same conclusion, cannot use the pi. Okay. Again, can never conclude H0 is true. So that's the reason why whatever the question is asked should be go to H1. H1 is what the question is asking. Because if H0 is what the question is asked, we can never sure H0 is true or not. So this is one thing. The other thing is, again, equality line goes with the null hypothesis, H0. Okay, so that's the two main things to help us to set up H0 and H1. So when a result has a small p-value, the p-value less than alpha, we say it is statistically significant. Okay, but here says significant doesn't mean it is important. Okay. All right. The next couple of slides of today, we talk about hypothesis test, which we discussed here in chapter 6, and the confidence interval we discussed in chapter 5. Okay, remember section 5.1 is large sample confidence interval for population mean. So large N for population mean. And 6.1 is hypothesis test, large sample hypothesis test for population mean. Okay. Both confidence interval and hypothesis test concern about determining plausible value for population mean or other things, such as proportion or difference between proportions, as we discussed in different section of chapter 5. Okay, so same thing here in chapter 6. For hypothesis test, we specify particular values, okay, which is defined as A0, the null hypothesis. Okay, for example, the null hypothesis is this. Okay. Right, a certain value, such as mu0, and determine if that value is plausible by comparing p-value and alpha. Okay, p-value and alpha. Confidence interval for example, for population mean, can be seen as collection of all values for mean value that meet a certain criteria of plausibility. Okay, so the collection of all values actually is the range. Okay, remember we say, for example, 95% confidence interval, we get a range, for example, 14.1 to 15.9. So that's the range, and within the range, that's the confidence interval. Okay. And the correlation between confidence interval and hypothesis is very close. Okay, and actually here state the values contained within a two-sided level of 100%, 1 minus alpha, 101 times 1 minus alpha percent confidence interval is exactly the same value for which the p-value of a two-tailed hypothesis will be greater than alpha. Okay, so all hypothesis tests and confidence interval, they based on the same distribution for the same condition. Okay. Okay, for example, in section 1 in chapter 5 and 6, we all use table 8.2. Okay. For hypothesis tests, we use this to calculate the p-value. Okay. For confidence interval, that's the middle part. Okay. So confidence interval and hypothesis test will fit each other exactly like this. The textbook will give a proof about this, but here just remember the equation and alpha used in confidence interval and hypothesis test are almost the same for the same situation, such as large sample population mean. All right. Okay, and yeah, that's it for today.